Welcome to Data Science with EJD. In this video, we're talking about XGBoost, and LightGBM. That's under Advanced Supervised Learning. We've been looking at supervised learning all this while, talking about classification and regression. So under this advanced supervised learning, we are looking at some advanced ways of classifying and, even regressing, right? So let's see. Here, our learning objective is to gain a deep understanding of gradient boosting concepts and two of its leading implementation. So generally, we are in the last video we looked at ensemble methods, which involved things like voting, bagging, and boosting. So here we are focusing on boosting in particular, and two of the top implementations for boosting, XGBoost and LightGBM. So we can learn to prepare and preprocess data for these models. And then we can apply and tune these models on the Kaggle Titanic dataset for classification. Then first of all, how do we let's understand gradient boosting. We already have an idea based on the last video where we talked about ensemble methods. So ensemble learning, that is, what is gradient boosting? Of course, an assembly technique that builds models sequentially to reduce prediction errors. That was exactly the last part of ensemble learning that we saw in the last video. So each new model fits on the residuals or errors of the combined previous models. So we use gradient descent to optimize the loss function and typically employs decision trees as weak learners. Then why do we use gradient boosting? Because it has high predictive power, it is robust to different data types, and can handle complex nonlinear relationships. So, introduction to XGBoost, which is one of the implementations of boosting. XGBoost stands for Extreme Gradient Boosting, which was developed by Tianqi Chen, and it is an efficient and scalable implementation of gradient boosting. I think Tianqi Chen was a Microsoft staff or so, I'm not too sure. But he developed that. Then, core features of XGBoosts. So first of all, you have tree construction, where you have level-wise growth, which splits trees level by level. I think that's why um, the base model or so is decision tree or so. If you remember what we did in the last video, we always had that decision tree thing, decision tree classifier, like the as a base model, and then we can talk about regularization, where L1 and L2 regularization can help to reduce overfitting. We've already seen ridge and lasso; those are L1 and L2 regularizations to reduce overfitting. We have handling missing values, automatically learns best direction for missing data. Then there's parallel processing, which supports multi-threading for faster training. There's flexibility, which is where we have customizable loss function and evaluation metrics. There's also early stopping, which stops training early. So it stops training early if performance doesn't improve, right? Then there's cross-platform support. So you have APIs for Python, R, Java, C++, Julia, and more. So you have cross-platform stuff like this. Um, okay. Now let's talk about advantages and limitations of XGBoost. The advantages include the fact that it is robust, it is widely adopted, it is excellent in documentation, it is good for small to medium data sets. The limitation is that it's slightly slower than light GBM on large data sets. Level-wise growth can be less efficient. So basically, if you have small data sets, you go small to medium, you go for XGBoost. But if you have large data sets, light GBM is where you go. Okay, so we have light GBM now. Introduction to light GBM. Light GBM is a gradient boosting framework developed by Microsoft, and it is designed for speed and efficiency, particularly on large data sets. So if you're talking about boosting and you're working with small data sets, go XGBoost. Large data set, go light GBM. So core features of light GBM, then we have tree construction. So it is leaf-wise, it has leaf-wise growth with depth limitation. It splits leaf with maximum gain. Then there's histogram-based algorithm. It's used bins for continuous values to speed up training and reduce memory. Then there's native categorical support, where so it directly supports categorical features without one hot encoding. I think that's usually a problem in machine learning, right? So if you have categorical features, you may have to encode one hot or whatever. You have to do some kind of encoding to get a better result, right? Then GPU support, it allows GPU acceleration for even faster training. Then there's early stopping also, which supports early stopping supports early stopping to prevent overfitting. Then there's efficient memory use because it is optimized for lower memory consumption. Okay, advantages and limitations for light GBM. So it's faster training advantages, right? Faster training, better accuracy in many cases due to leaf-wise splits, and it is better for large-scale data, like we've been saying. The limitations include the fact that it has leaf-wise goods, which can cause overfitting on small data sets if not tuned properly. Of course, we from what we've learned already, if you have small data sets, XGBoost is what you need. So let's look at some systematic workflow where we apply XGBoost and LightGBM on the Titanic dataset. So we've been using the Titanic dataset since we dealt with data analysis with Python. So let's talk about data loading and exploration. So we use the Titanic dataset from Seaborn for convenience. It's similar to the Kaggle dataset, right? So here we need for Seaborn, right? So it is inside Seaborn. We can load the data sets. We've used this a lot, right? So this is like an inbuilt data set in Python. So so far we've seen that we can access data sets from Seaborn, from scikit-learn, and from maybe from Kaggle and all these other external sources. So here now we can upload this. So DF will help us to visualize. So this is a data set we've worked with a lot, right? So and they are missing data and things like that. So all this NAN you see talks about missing data. So because of that, we need to do some pre-processing, like handle missing values, select relevant features, encode categorical variables. Just like I said, for machine learning, you may need to encode categorical variables for more efficient training, right? So here now, SKLN model selection, train test split, SKLN preprocessing, label encoder, SKLN imputes. You need a simple imputer. Now, the imputer here is going to help us impute values for anything that is missing, right? So you can drop irrelevant columns. So df.drop, we don't need them back down, whether somebody is alive or not, whether it's adult, male, or deck. So that's what line 6 is doing. So we are preprocessing now. So we drop columns we don't need. Then we can handle missing values. So for missing ages now, we fill not available ages with the median age, right? All through. Then for DF embarked, so we fill the missing embarked places with the mode, the most common place where people embarked from. I mean, that may not be 100% correct, but at least there's a higher chance that somebody embarked from that place. So we use the mode in that situation. Then we can also encode categorical features like so we have label calls, df does select the types. So anywhere you have object types, right, for columns, so you have le to now be label encoder. So you say for call in label calls, df code just become le dot fit transform df code. So that way you can do, so this le now will do the label encoding automatically. So like for several columns that have missing, that have object type values like that, then you can do the split features and target. So for the X now, talking about the features, it's a df drop survive. So because we want to predict the survived class based on the other features, so we drop the survived and then we transfer that to Y, to the target. So X now is your X is your targets, and Y, no, X are your features, sorry, not target. X are your features and Y is your target. Then we do the train, the split, X train, X test, Y train, Y test. The usual train test split, XY test size 20 because you're using 80% for training. Random state to ensure that things don't change no matter how many times you run. So we run this and then it's done. Of course, we just want to visualize, like I always like to do. We just want to visualize your X and Y for this for the sake of it. Or I mean, if it's, of course, you expect to have done your, so now you see the survived has been dropped because we dropped it, and then we have removed some things we don't need. So the survived thing is not here now, and we've dropped some things we don't need. So we only have what we need now. And then you can also see the Y like this. So that talks about the survived class. So I think 0 is for not survived, Y is for survive. So you can now prepare train and validation sets. So of course, if you want to, for XGBoost implementation, we are doing XGBoost and LightGBM implementation. So for XGBoost implementation, you need to install the library. All right. So if you don't install the library, you won't be able to import it because it's not inbuilt in Python. I had already installed. That's why it's telling me requirements already satisfied. If you're installing it for the first time, it will take a bit of time and then it will run. And then now so we need pandas and XGBoost that we've just uploaded, that we just installed. So we import XGBoost as XGB. So from SKLM metrics, we need the accuracy score because we are classifying basically. Then from one how to encode categorical variables, xtrain encoded, we have pd.getDom is xtrain, xtest encoded, pd.getDom is xtest. Then we can align the columns. So we have xtrain encoded, xtest encoded, xtrain encoded dot align, xtest encoded. So you join at the left, it's like you're putting all these things together. Then you can initialize and train model without deprecated parameter. So you have XGB model equals XGB.XGB classifier. Evaluate metric is log loss. Um, and then XGB model dot fit. This is where you fit the model to the data. So X train encoded and Y train. Then you can now predict and evaluate. So Y pred XGB is XGB model dot predict X test encoded. So you print the XGBoost accuracy. So we run this and we get an accuracy of 0.79, right? Then that's the XGBoost implementation. What about the LightGBM implementation? So you see the accuracy is 0.79. So for LightGBM, you have to install it. Pip install LightGBM. I did it before, that's why it's telling me requirements already satisfied. If you're doing it for the first time, it will take a bit of time and then it will install. And then here you can now say import LightGBM as LGB, then LGB model equals LGB dot LGBM classifier, LGB model dot fit. That's line 4, that's where you fit the model. The that's where you train the model with the data, and then you can predict and evaluate ypred LGB underscore model dot predict x test. Then you print the accuracy for this. So see, XGBoost give us 0.79. Here, let's see what it gives. It gives maybe something a bit higher. So it takes some time and then it goes. No spotter fleet, blah, blah, blah. It keeps going and finally gives us 0.84, which is better than XGBoost. Then you may want to do some hyperparameter tuning. So here, if you use using grid search CV with XGBoost, so you see XGBoost performs less than LightGBM 0.79, right? And this one is 0.84, right? So here to do some hyperparameter tuning, so import pandas as PD, sklearn proposing ordinal encoder. So you now have identify categorical columns. So categorical columns is xtrain.select data types includes category.columns. So, and then you want to convert these categorical columns to ordinal numbers. So encoder is now ordinal encoder. So xtrain categorical columns that you've identified here, you now say encode.fit transform xtrain categorical columns. So if you do this, then we expect to have like a better performance for XGBoosts. So then you can now see we can do the comparison like that. So we have from sklearn metrics import classification. Does this really have any impact? I doubt it. So here we are comparing and interpreting LightGBM and XGBoost. So from sklearn metrics import classification report and confusion matrix. Since you are doing a classification job, so you have XGBoost report, classification report, ytest ypred XGB, then ytest ypred LGB in this case. So we have that. So generally speaking, you see all the precision recall and everything, you have it going there. So of course, generally speaking, you have LGBM doing better, LightGBM doing better than XGBoost. So I think this hyperparameter tuning, um, I don't think, excuse me, I don't think it has done anything better, except that yeah, probably that is what has made this better also. Okay. So for observations, now both models can achieve strong accuracy on the Titanic dataset. LightGBM tends to be faster with better memory efficiency. Model choice can depend on data size, feature types, and tuning capabilities. So when you are done with all this, right, if adapting to Kaggle format, so in case you are doing a Kaggle competition, you can simulate with this CSV export, right? So you remember how we used to, you can read data from CSV, JSON, even SQL, right? And probably even Excel. But you can also, when you get some data, you can also write it back to any of those formats. So if you're doing Kaggle style, you may want to try this also. If you say submission, maybe you're submitting in a competition. So submission equals pd.data frame, passenger ID, that's what you get from xtest.index and survived ypred LGB, then submission to CSV. Now you see this submission.csv now, it doesn't already exist in my folder. Like this is my folder now. So there's nothing like submission here. right? There's nothing like submission here. That is a CSV file. So if I run this now, it automatically creates it. So I run this and it's done. So I can come back here into my folder, and now I see this submission thing that was created at 3:13. It is 3:13 a.m. So I have this now. Click this. So it gives us the passenger number, passenger ID, and whether they survive. So passenger 709, 439, 840 did not survive. 720 survived, and so on and so forth. So we can follow that through. I think it's all like 180 passengers information that we have right there. Okay. So some key takeaways. Gradient boosting is powerful for structured or tabular data. XGBoost and LightGBM are top tier tools for production and competitions, and their proper processing and tuning are essential for best results. So, I mean, I didn't delve deeply into, uh, you know, proper processing and tuning for both of these ones. So, maybe in a subsequent video, we might talk about that. So, with this, we come to the end of this video. Let me know how helpful this is for you, and if there's something you like on to try out, feel very free to let me know. If you have subscribed to the channel, thank you. If you haven't subscribed, please go ahead and subscribe, and be sure to be sure to hit the notification bell so you can always get alerted each time a new video is released. On my channel, you can become a member, whether at bronze access level or silver access or gold access, and this come with different level of special privileges. Feel free to avail yourself of that and see how we can interact on this channel. Be sure to like and share this video and all that so that more people can have access to the great content I have going on here. Till I come your way again, keep doing data right. Bye.